All right, so now you've seen some videos on how to find asymptotes. I want to show you a slightly different way to think about asymptotes to help you figure out what's going on. And we're going to take advantage of polynomial long division to do so. So let's look at one of the examples from the Actually, first, let's go ahead and let's just remember that when we look at the graph y equals 1 over x, this is the inverse graph or inverse multiplicative inverse graph. This looks something like this. And if you notice, this function has two asymptotes, the vertical asymptote at x equal to 0 and the horizontal asymptote at y equal to 0. So go ahead and keep that in mind, that this has this asymptotic structure to it. That is, when we go to infinity in x, y goes to 0 from the positive side. When we go to 0, if x goes to 0 from the positive side, y goes to infinity. If x goes to 0 from the negative side, y goes to negative infinity. And as x goes to negative infinity, y goes to 0 from the negative side. So if we look at a function like f of x is equal to 2x minus 5 over 3x plus 4, we can actually apply polynomial long division to this. So I'm going to do that right here. We're going to take 2x minus 5, and we're going to divide into that 3x plus 4. Now, if we look at this, you would say, oh, 3x does not go into 2x, so we're done. But in fact, you can find something that multiplies by 3x to give you 2x. That's the fraction 2/3. And if we do that, we have 2/3 times 3x, so the 3's cancel and we have 2x left over. And then we have 4 times 2/3, that's 8/3. And what we're going to do is we're going to subtract that whole expression. So like before, subtraction is going to be distribute like so. So if we look at that, we have a 0, and then we have negative 5 minus 8/3. That's adding fractions. So let's see, negative 15 over 3, so negative 23 over 3. And so we have a remainder of negative 23 over 3. So what that tells us is that if we were to solve for this right here and rewrite this, this over this, 2x minus 5 over 3x plus 4 is equal to 2/3 plus a remainder of negative 23 over 3 of 3x plus 4. Now, it's not immediately obvious from looking at this, but this is just a transformation of this graph. If we look at this plus 4 and this times 3 are going to horizontally shift and then stretch and compress the graph. Let's not worry about the order. This is going to vertically reflect the graph, and it's also going to vertically stretch the graph, and then this is going to shift it up. So that's a lot of things to keep track of. But if we look at this for a minute, we can just ask, well, what happens as x goes to infinity or x goes to negative infinity? Well, as x gets larger and larger, that is, it's going to infinity, we're dividing by something that gets bigger and bigger and bigger, so this whole thing is getting closer and closer to 0. So if we look at this part's getting closer to 0, this is just staying 2/3. So that tells us that we have an asymptote as x goes to infinity, y goes to 2/3. So in a situation where the x is going to infinity or negative infinity, that gives us a horizontal asymptote. Now, if we look at the vertical asymptote, we need to figure out how these horizontal transformations shift things around. We know that it's something along those lines, but we can actually do something much simpler. We can just simply solve for when it's equal to 0. And if you do that by subtracting 4 from both sides and then dividing both sides by 3, you get x is equal to negative 4/3. And that's going to be where this vertical line, x equal to 0, goes to when you shift left by 4 and then horizontally compress by a factor of 3. And so that'll give us the vertical asymptote. And so in many situations, our rational functions can be simplified using polynomial long division in order to give us an easier way to see what kind of asymptotes we have. Okay, so here's another function that we looked at a minute ago, and we know that it has a vertical asymptote at x equal to 1 because we can't put 1 in, and in fact, if you look at this doesn't go to 0 either, so there's no cancellation. And then there's this vague rule that this doesn't have a horizontal asymptote because the power in the numerator is greater than the power in the denominator. Now that's completely correct, but this still has an asymptote. It's just not a horizontal asymptote, that is a horizontal line that it gets close to in some limit. So let's go ahead and let's do long division on this and see what we yield. Now, we're going to divide x minus 1 into x squared plus 3. Now, you should notice that I put a gap there. And the reason for that is, if you notice, these terms are 1 power of x off each other, and these terms are not 1 power of x off each other. So what we're going to do is we're going to add 0 in a very clever looking way. So 0 times any number is 0. So we just put it in there, so we added nothing, but this will make the long division more clean, and we'll avoid some pitfalls that come up. So if we look at this, we still need to get x into x squared, so that means that we need an x. So then we have x squared minus x. Going to take that and we're going to subtract it, which means that we're going to distribute the negative. So x squared minus x squared is 0, and then 0x plus x is equal to x. So now you can see why we included that 0 there. It's so that we lined up an x term over under another x term. If that x had ended up under that 3, you would have x plus 3, which I guess is not so bad, but this sort of avoids some notational errors. So then we drop the 3, so we get x plus 3. Again, x goes into x exactly 1 time. So then we take 1 times x and then 1 times negative 1. We subtract that. And so then we get 0 plus 4. Okay, checking my notes, make sure I didn't make any mistakes. So then that's remainder 4. So what this tells us is that if I take x squared plus 3 and I divide by x minus 1, I get x plus 1 plus 4 over x minus 1. Now this is a little bit trickier than what we saw before, but let's just think about what's going on with this for a minute. So this function is just that 1 over x graph transformed. So it's going to look something like, well, we could just do it, right? So minus 1 from the x, that's going to be before we take the inverse, multiplicative inverse, so that's going to be a horizontal action. Minusing 1, well, usually that's the negative direction, but it's horizontal, so we do the inverse and go right. So we're going to have an asymptote at x equal to 1. And then it's also going to be vertically stretched by 4, which is going to stretch it out, but it doesn't change the asymptote y equals 0. And so then we get something that looks like this. So that's our first graph. Now if we look at that, there's also an x plus 1 here. So let's just graph that for a minute. I'm going to do that as a dotted line. And if I go ahead and graph that graph, well, what will happen? Well, it's got a y-intercept of 1, and it's got a slope of 1, so it looks something like this. So this is y is equal to x plus 1, but this isn't the function either, so what I'm going to do is I'm going to just dotted line it. Okay. Now what we're going to do is we're going to take this graph and we're going to add the y value. So at every x we look at, we add a y value here. Now if you notice, we shouldn't get anything at x equal to 1. So let's go ahead and do that. And if we look what would happen, well, this one's going up and up and up, so it should still go up and up and up. But then if we look at it, it's going sort of horizontal. But what we do is we take something getting close to 0, and then we add x plus 1 to it. So it's going to get close to x plus 1, because x plus 1 plus something close to 0 is just close to x plus 1. A similar thing happens over here. As we approach x equals to 1 from the right, this goes to negative infinity. And what happens at x plus 1 at 1 is just going to be 2. So 2 plus negative infinity is going to be somewhere in the neighborhood of negative infinity. And then likewise, this stays below the line y equals 0, but it gets close to it. So then this will stay below the line y equals x plus 1, but get close to it. And so in this case, this doesn't have a horizontal asymptote. If you tried to draw a horizontal line, this will fly away that way and fly away that way. But it will get close to this line x plus 1, because if we look at this function, it's whatever x plus 1 is. And as x gets larger and larger, that means we're taking it either to positive infinity or negative infinity. We're adding something smaller and smaller and smaller. So this function is actually getting really close to x plus 1. So in the situations that you have a higher power above in the numerator than in the denominator, it's not that there aren't any other asymptotes. It's just that your asymptote is going to be some other line or possibly some other curve.